Welcome to the mass transfer course. Today will be lecture 10, and here we are discussing about the convective mass transfer and mass transfer coefficients. In lecture 9 we have calculated different types of mass transfer coefficients, and this was the summary set. Diffusion of A through non-diffusing B, okay, then gas phase mass transfer coefficient, this is the Kgpa minus Pa2 corresponding expression of Kg, then Ky Ya1 minus Y2, that's corresponding expression of Ky, Kc Ca1 C2 for this one. And for liquid phase, Kl Ca1 minus Ca2, this was the expression for Kl, and Kx Xa1 minus Xa2, and this was the expression for the Kx. Similarly, we have calculated for equimolar counter diffusion that all are prime, Kg prime, the partial pressure difference, okay, then this was the expression of Kg prime. Ky prime, our driving force is the mole fraction, and this was the expression for the K prime y. Kc prime, where driving force is molar concentration, and this is the expression of the Kc prime. And we discuss about the units of the mass transfer coefficient. Whatever the driving forces, that will be added in denominator. Other things are nothing but your parts. And for liquid phase, Kl prime, Ca molar concentration driving, this is the expression for the Kl prime, and driving force in terms of mole fraction in liquid phase, Kx prime, this is the expression. And if you know one, then you can calculate the other through this conversion factor. This table you have to digest, otherwise you cannot deal with the mass transfer coefficients or convective mass transfer problems. If you want to deal with the mass transfer, then you have to understand this, otherwise it is not possible, because here complexity is much higher. In case of heat transfer, you have only one transfer coefficient, but here you have to deal with 10. To make it better understanding, today will solve 3 problems based on the mass transfer coefficients. That is problem 1, that determine the relation between gas phase mass transfer coefficient Kg with K capital Y. Capital Y is, this is the mass transfer coefficient, where driving force is your mole ratio. Last day we discussed. So in case of this, what will be that your Na will be this will be small k capital Y. Small k capital Y means driving force is mole ratio Y1 minus Y2. Understand? Ya1 minus Ya2. Okay, so this will be our expression. So driving force So now we have to determine, and this is kg, where kg means air pressure, this is driving force is in terms of partial pressure. So Na equal to kg into Pa1 minus Pa2. Now we have to determine the relation between kg and capital K, capital 1. Now this driving force Y1 minus Y2, Y1 capital that YA, okay, capital YA, I can write small YA mole fraction by 1 minus 1 minus YA. So YA, this is mole fraction, this relation last day we discussed. So Y equal to small p A by total friction, and 1 minus YA equal to P minus PA minus P. This will not be there. Okay. This will not be. So then it will come what? It will come PA P. Okay, this will come P. This is P minus PA, and PP will cancel out. So this is your capital Y A, this equal to this, that is converting ultimately, it is coming to your PA partial pressure of by total P minus P. So this thing I am writing here. So for now Y1 PA1 P minus PA1, okay, for this is for Y1. For Y2 this is PA2 P minus PA2, same expression, it will be this. Now if you write this one, this will be multiplied. So P into PA1, okay, minus P1 P2 minus P into PA2, and this will be plus. So this will cancel out. So P equal to P into PA1 minus PA2, and P minus PA1 equal to PB1, and P minus PA2, that is a PB2. Okay. So capital Y A1 minus capital Y, this driving force, and here the driving force is in terms of partial pressure with this factor. Okay, so PA1 minus PA2 equal to Y1 equal to this. Now we have kg equal to PA1 minus PA2. Now what is kg? Kg equal to DABP RT delta PBM into PA1. Okay. Now this expression I can express in terms of this. So this will be there. And this is equal to capital Y, this that coefficient into this. So capital Y equal to this term into this term. So our capital Y will be kg into this term, because if you multiply, so capital kg equal to this and this equal to this. So now if you multiply with this one, this will be this. So capital Y equal to kg into this term. This is the relation between capital Y and K capital Y and kg. Similarly, any mass transfer coefficient you can calculate. Already we have done it before, but that day we did not calculate this one. That's why we have calculated. This is one problem. Now problem 2. Ammonia A is being absorbed in water from a mixture with nitrogen. So ammonia is getting absorbed from gas phase to liquid phase. So gas phase is ammonia and nitrogen, A and B, and now ammonia is getting absorbed in water. So in this case nitrogen is non-diffusing to water. So this is the case where diffusion of A through non-diffusing B. The partial pressure of the solid in the bulk is 40 mmHg. Okay. And that at the gas liquid interface is negligible. It means what? Means at gas liquid interface the concentration of ammonia is very small. That means ammonia affinity, absorption affinity of water to ammonia is so high. Whenever it will come, it will automatically come to the water. That's why this is negligible. Diffusion occurs through a stagnant film thickness of 1 millimeter. So here the film thickness is given to you. One, you are lucky. Okay, and you should understand. You should see the unit. Generally, that thickness is in millimeter, 1 millimeter, 2 millimeter. So it is very small. The total pressure is 1 atmosphere, and partial, that is the partial pressure. Okay, and the temperature is at 25 degrees. Diffusivity of ammonia in nitrogen is 0.023 centimeters per square. But its unit is given centimeters per second. So if I calculate this in meters, in MK, so I have to, accordingly I have to make this conversion. So centimeter square to meter square, I can write 0.023 into 10 to the power minus 4 meter square, or then 2.3 into 10 to the power minus 5 meter square per second. Accordingly we have can calculate the absorption flux of ammonia as well as the mass transfer coefficient small kg, ky, kc, okay, small k capital Y, fg, because this is the happening the mass transfer coefficient gas phase. Okay, then these are the possible thing, small kg, small ky, small kc. This is the k small capital Y, it is the where driving force in terms of mole ratio, and fg is a type of mass transfer force. You have to calculate this. So here ammonia A diffuses through non-diffusing B. Now we know that for a stagnant film or molecular diffusion, this is the thing. I can calculate the flux through molecular diffusion. This is, or you can put this delta. Okay, delta, but here delta is given. Whether you are using this equation, it does not matter. Now dV equal to, so I will do that is in semi square per second, then I calculate in meter square per second. P equal to 1 atmosphere, T equal to 298 Kelvin, L equal to 1 millimeter equal to 10 to the power minus 3 meter, P0 is 40 mm, so 40 by 760 equal to 0.05263 atmosphere. This is the, and PL that is equal to at the interface, this is equal to 0. Now I calculate this one, Na equal to DAB equal to 2.3 into 10 to the power minus 5, P equal to 1 atmosphere, and if I put this 1 atmosphere, that's why I am putting this liter atmosphere. Okay, then this is the 298 into 10 to the power minus 3. Okay, L equal to 10 to the power 2 another ln P 1 minus 0, L equal to 0, this. So now it is coming, this is kilojoule per meter square. So unit of R is meter cube atmosphere per kilomole degree Kelvin. Okay, so this is the thing. So unit you have to deal this unit, you should be careful, and I'm telling you repeatedly what will be the value of R, you should be careful. If it is a bar, then you have to multiply that, then it will come 0.083 something will come. Okay, that we discuss. So Na equal to 5.083 into 10 to the power minus 5 kilomole per meter square second. That is the absorption flux of air. Now Kg equal to what? Na by this Pa0 minus Pl. I know this Na. Na equal, then Pa0 equal to this. This is the thing, and Pl equal to 0. So this will be your this. So kilojoule meter square second per atmosphere. Okay, 9.658 into 10 to the power minus 4 kilomole per meter square. But here this unit is atmosphere. That you have to mention. Unit you have to mention kg. Ky Na by this. See, Na y equal to P by P. P equal to 1 atmosphere. So in this case, Ya will be Pa. So that's why this by the minus. So this thing it will be same. Ky also will be same, because Kg numerically it will be same, but in this case it will be delta y. Kc equal to this by this. Now Ca0 equal to Pa0 by Rt and Cl equal to 0. So this my Na into Pa0 into R 0.8 into 2. So this will come 0.02363 kilomole per meter square second. This is delta C, that is kilomole per meter. In this case, that will be, so unit here in this case delta Y, this is delta C kilomole, and in this case delta P, that is in atmosphere. That you have to mention. Now Fg equal to Kg into ppm. I know, we know this one already, we did given. So ppm equal to Pb1, that is 0, okay, 1, okay, and when it will Pl equal to 0, then Pb equal to P, that is 1, and when P this is equal to Pl equal to this, then 1 minus this. So this minus this by ln this. So this will be ppm will be 9734 atmosphere. So Fg equal to this, okay, whatever this factor is Kg we have calculated, okay, this one, okay, divided by into this. So then it will be kilomole per meter square. Atmosphere we have calculated, so then you know that unit will go. This will not be there. So mass transfer coefficient Kg, Ky, Kc can. Yes. I will calculate it this way, but you can calculate it other way also. Okay. So here primarily we are focusing how to calculate different type of mass transfer coefficient where delta is given. Okay. Here in this case delta I am providing. Okay, but next will after some time it will not be provided to you. You have to calculate that one also, because delta, boundary layer thickness, is the most critical factor here, because already we discussed other terms can be calculated easily or easily available. Now problem 3. So problem 2 we have discussed with one problem where diffusion of A through non-diffusing 3. In problem 3 we will discuss one problem equimolar counter diffusion. Okay, the gas phase reaction A to B occurs on a surface of catalyst in the form of a wire gauge. Okay, so A to B reaction is happening, okay, in a porous catalyst. So equimolar, so A is diffusing through the pores and B is coming out. So this is a equimolar counter diffusion case. Okay, The bulk concentration of species A is 0.002 kilomole per meter cube. Okay, bulk concentration is given, that and that of the reaction A is measured at 0.08 kilomole per hour meter square. Although they are telling this is rate, but this is the flux, kilomole per meter square hour, but it is instead of second, it is in terms of, so rate or A is given. In this case, reaction rate is measured, this reaction rate is, but actually this is the flux. Okay, that is kilomole per meter square, but it is in R. If this reaction is instantaneous means when it will reach to the surface, usually it will consume. That means the rate of reaction is faster than your diffusion rate. So that means concentration at the surface will be 0. So bulk concentration is this CAB, and CAS, that will be the 0. And the interdiffusional resistance to the transport of the reactive species from bulk to the catalyst to the surface offered by a stagnant film of the gas. Okay, that is one film is there. Now you have to calculate the thickness of the film. In previous problem, we have given the thickness, film thickness, you calculated the flux. In this case, flux is given, you have to calculate the film thickness. The mass transfer coefficients, the Kg dash and Ky dash in this case. Okay. The concentration of a halfway the gas film. The total pressure in this case 1.5 bar. That time it was atmosphere. In problem 2 it is in bar, but it is 1. Temperature 250 degrees centigrade. dV is 0.16 semi-square per second. That means it will be 1.6 into 10 to the power minus 5 meter square per second. But this is given at 1 bar temperature and the 100 degrees centigrade. But your reaction condition is 250 degrees centigrade and 1.5 bar. So here when you use this dV for this system, so you have to calculate this dV at this bar at this temperature, and for that one we have the relations. We know that temperature to 155 and P 1 by bar. That thing we have to taken care here. So your calculation of dV, because dV here in which condition is given, but your reaction condition is different. So you have to calculate this dV from at this reaction condition. Okay, this is the problem. So this is the equimolar counter diffusion problem, where here flux is given and other parameters are given. You have to calculate the mainly thickness of the film, and thereafter you have to calculate the mass transfer coefficient. So this is a case of equimolar counter diffusion of the reactant A and product B through stagnant film. Rate of reaction per unit area, that is the flux of A, Na equal to Kc dash Cb minus Cs. A is given, kilomole per meter square hour. Bulk concentration is this. Okay, so bulk concentration is this. Concentration at the surface of the catalyst C equal to 0, that is because when it is distinct to the instantaneous reaction means fast reaction. Already we discussed this concept. So when Ca will be at the surface, this is 0. See what is the concentration from concept you have to understand. Where Ca will be 0, where it will be. Okay, already we discussed all these things. Since the reaction is instantaneous, T equal will be 270 this and P equal to this one. Okay, this is the condition. Now this is the MA, kilomole per meter square hour, Kc, and this is the my driving force. So Kc equal to this by this, then meter per hour. Okay, always write the unit, it will help you. Is kilomole per meter square hour, then kilomole per hour, then meter per hour. Okay, then meter per second, 40 meter per hour, then this is the meter per second, Kc dash. So Kc dash equal to dAB by delta. So isn't it? Kc we have calculated, and if we can calculate dAB, then at this reaction condition that will be there. Now dAB will be what? So 0.016 semi square per second, or 1.6 into 10 to the power minus 5 meters per hour. Pressure is high. Okay, so this is the pressure effect. So that was at 1 atmosphere. If 1.5 atmosphere, that will be, you know, the pressure high means this will be, that is the relation. Okay, and if it is temperature, you have given at 100 degree when 73, and then 3523 reaction that into the what 25. So if you always you should consider that dAB you have to calculate the process condition. That value will be given. People will do some experiment at a particular temperature, and they will report this one. Then using this correlation, we have to calculate the dB at process condition, and this is the way. For gas phase, we know this relation, so that's why we are putting this. Okay. So finally, dAB will be 1.77 into 10 to the power minus 5 meter square by 7. So delta equal to dAB this by Kc. So delta equal to 1.6 millimeter. Okay, but you should consider. So these are the typical values of boundary layer thickness. Just 1 millimeter, 2 centimeter, 1.5 millimeter, 2 millimeter. This is the range. That is very important parameter. You should understand. Calculating of this is very small. It is that's theoretically visualization of this boundary is very difficult. Now, if you know this one, on kg you know dAB by RT delta. Okay, dAB okay. Now dAB by delta, this is equal to this Kc. dAB by delta equal to Kc. That's why I put dAB by delta. I put directly this value, Kc value. Okay, or you can put dAB this and delta, then also it will come. Okay, into R. Then if you see, I have changed this 0.08, not 82831, that factor, you know, atmosphere to that bar, you have to change this. So this will be your kilomole per meter square second bar. Okay, this will be in bar. Okay, and ky dash over dAB P by RT delta. Okay, so then it will be dAB delta equal to this and RT. Okay, so this term is nothing but your this term. So this term is there, only the pressure term. So this is kilomole per meter square second. Okay, so I calculated kg dash ky prime. Now we have to calculate what is the concentration halfway. Okay, if you see the last question, the concentration of a halfway the gas film. So my gas film is 1.6 millimeter, and what is the concentration halfway means after point, what is the concentration at 0.8 millimeter. See, if you can remember this one, equimolar counter diffusion, that concentration will be linear concentration profile. That will not be nonlinear. Okay. In case of diffusion of A through non-diffusing way, that concentration profile will be the nonlinear. You can remember that concentration profile part in molecular diffusion. So if it is a layer, so that will be CO at halfway will be just what is bulk and this surface by 2. So bulk is this, surface by 2 by 2, this will be this. Okay, 0.001. Okay, so in today's lectures we have solved 3 problems. First problem was what is the relative between K capital Y and Kg. Okay, Kg and K capital Y. Second problem we have addressed one diffusion of A through non-diffusing B where delta was given and we calculate the flux and different type of mass transfer coefficient with this correlation. And third problem we have done equimolar counter diffusion where flux was given, then we have calculated the film thickness. Where either flux or film thickness is given, and then thereafter we can calculate the other mass transfer coefficient from the equations. But practical problem will be like this. Your film thickness also will not be given, and flux also will not be given. These two you have to calculate. Here, between flux and thickness delta, one is given, other you are calculating. It is very easy based on what we have studied last. But in practical problem, you have to calculate the flux, that is your motto, because you want the higher flux, so you have to calculate that way. And now you understand to calculate the flux, you know the mass transfer coefficient. In mass transfer coefficient, delta is there. Other than delta, other things are easy to calculate. At the process condition, you will get it easily. But delta, still now we are giving the delta, but in reality, you have to calculate this delta, or you have to calculate the mass transfer coefficient directly. So this thing we will address in the next lecture. Thank you for your attention. Bye.